In this screencast, we're going to look at what are called moments of inertia, or in some places, second moments of inertia. The idea is we're going to go back to physics a little, and we're going to look at an equation for kinetic energy. Kinetic energy in a physics class you'll often derive as 1/2 mv squared, where m is the mass of an object and v is the velocity. Anything in motion has attached to it a kinetic energy, and this is an equation people discovered which you can use to generate how much kinetic energy is there if you're moving at a certain speed with a certain mass. Well, the idea we're going to be taking is what happens if you take some object, so an arc or something, and you decide to rotate that arc about an axis. What if you start rotating it? You take some object and you want to rotate it. Well, notice that the pieces close in are moving a lot more slowly than the pieces that are far out. So the velocity kind of depends on the radius out, how far you're going. And so what we're going to be doing is really we have a little bit of kinetic energy is equal to 1/2 times a little bit of mass. We're taking the arc and we're going to cut it up into a few pieces. And then we need to times each of that by the velocity of the arc. Well, if we keep the angular velocity the same, so the rate at which the angle's changing, we'll keep d theta dt, which is the angular velocity. We'll make sure that's constant. So whatever we're rotating, we're just going to rotate it around at the same speed, nonstop. This is often given with the symbol omega, or a w, and we're going to keep it constant. If we know that, how do we find the length of an arc? Well, you can find the length of an arc by taking the radius out, all right, this is radius out, times the angle traversed. Which means if you take the derivative of both sides with respect to t, notice that the radius stays the same as you go around, so I can leave that alone. But I do need to take the derivative with respect to time, which means this number here, which is our speed, is equal to the radius times the angular velocity. So I'm going to take this quantity and I'm going to replace it with that. Over here I've got a little bit of kinetic energy is found by taking 1/2 times a little bit of mass times a radius times an omega squared. And now I'm going to find out, first of all, the little piece of mass changes based on the bit of the curve I'm on. The radius also changes based on the curve I'm on, but the omega is kept constant. So I'm going to pull the 1/2 omega squared up front, and then the things that are changing are the radius and the little bits of mass. That's how you get a little bit of kinetic energy. If you want to get kinetic energy, you should then add up the little bits of kinetic energy. If you add up the little bits of kinetic energy, you can pull the constants out. So we've got a 1/2 omega squared, integrate, and then I've got the radius of rotation, whatever the distance is to the arc, times, oh, that needs to be, forgot to square the radius here. The radius should be squared times a little bit of mass. This quantity inside the integral is given a name. It's called the inertia. Or it's called the moment of inertia. Or sometimes called the second moment of inertia. And so we can write this as 1/2 omega squared I. And I'm going to rewrite it once more as 1/2 I omega squared. If you now come back and look at the original problem, notice that inertia looks kind of like the mass if you replace the speed with the angular speed. And so we've got our velocity has been replaced with an angular velocity, and the mass was replaced by inertia. So you can think of inertia as a rotational mass. And that's the interpretation of it. We now want to actually show an example of how you compute a moment of inertia. So what we need is we need a curve and we need a density in order to do anything in here. So first, let's start with the density. The book will always give you the density. That's a problem that sometimes you have to figure out in a physics or engineering class. But for now, we're just going to assume it's known. We also need a curve. Let's take as our curve a parabola. So just a simple parabola. And we're going to rotate this parabola. We need some bounds. So let's have t go from -1 to 2. And we're going to rotate the thing about the x-axis. So we'll go from -1 up to 2, and let's take this curve and rotate it about the x-axis. In doing so, we'll generate some energy. So the radius of rotation, notice the radius is just the distance to that axis, which is y. So if I want the inertia about the x-axis, the idea is I need to integrate along the curve the radius squared dm. Well, in this case, the radius is the y value, so I'll square the y value with respect to mass and add those up. Well, the y values I've got. The y values are t squared. So I'll square those. I do need to find dm. How do you get dm? Well, to get dm, recall dm is delta ds, and that's delta r prime dt, which means I need to come back here and I need to find out what the magnitude of r prime is. So r prime is 1, 2t. The magnitude of r prime is, well, come over here now, it's the square root of 1 plus 4t squared, which means I know what ds is. It's the square root of 1 plus 4t squared dt. I really just need that quantity. I also need my delta, which I've got right here. So to get the dm, dm is my delta, x squared plus 3y, times the ds. Well, x is t, so I need to take x and square it, t squared plus 3y. 3 times y is t squared. That's my delta. And then I need to add in my ds, the square root of 1 plus 4t squared dt. Notice here's essentially my magnitude of r prime. This quantity here is my delta. This quantity here is my y squared. And that's it. I've got the moment of inertia about the x-axis. If I wanted the moment of inertia about the y-axis, then the idea is I would need to know the distance to the y-axis, which is x. So in that case, I would integrate x squared with respect to mass. And, oh, I forgot some bounds. I need bounds. Negative 1 to 2. Negative 1 to 2. The x value is just a t, so I'll take that and square it. And the dm is the same quantity. T squared plus 3t squared. Square root 1 plus 4t squared dt. Now, if I took this curve and I decided to rotate it about the origin, that quantity is called I.O. And how do you get I.O.? The idea is I need the radius to the origin, which is x squared plus y squared, square rooted. And then I got to square that with respect to mass. So really, it's just take the x value, square it, take the y value, square it. So I'll take the x value, square it, take the y value, square it. And then, again, take this entire amount, dm, and put it right there. That completes the screencast.